As we saw in our last video, that a current carrying conductor produces a magnetic field around it. It also affects the magnetic field of the compass kept nearby. But we also know by Newton's third law of motion that to every action there is an equal and opposite reaction. Here too the law is followed. If the current carrying conductor exerts a force on the magnet and the compass, then the same force is exerted on the conductor as well. But does it really make any sense? Yes, it is true. Let's perform an activity to understand this. To perform this activity, we need a horseshoe magnet, a piece of copper wire, a stand, a battery, a switch, and connecting wires. First of all, put the horseshoe magnet on the stand such that the north pole should be vertically above the south pole. Hang the copper wire between the poles of the magnet with the help of the stand and connect its ends with the positive and negative terminal of the battery. Put on the switch after completing the circuit. We can see the deflection in wire in one direction. The deflection can be seen till the switch is on. How is this even possible? What will happen if the direction of the current is changed? Let's do this too. It can be seen that the deflection changes its direction as we change the direction of the current. But the question is, why does this happen? Let's get into the explanation one by one. The reason behind the deflection is that magnetic field produced by current carrying wire gets in contact with the magnetic field of the magnet. Both of them exerted a force on each other, and due to this deflection, we could be able to see the deflection. We got to know the reason behind the deflection in the wire, but we didn't know the answer of why the direction of deflection changes as current changed its direction. Let's find out this answer in this section of the video. Looking into it closely, we can find a pattern here as well. We know that the direction of the magnetic field lines is from north to south. When the current was flowing in this direction, then the deflection was in this direction. If we rotate the picture, we'll get to know that all the three components are perpendicular to each other. The relation among force, electric current, and the magnetic field is known as Fleming's left-hand rule. This rule states that if we stretch the index finger, middle finger, and the thumb of the left hand such that all the three are mutually perpendicular to each other, then the index finger will point out towards the direction of the magnetic field, the middle finger will point out towards the direction of the current, and the thumb will show the direction of the force. If we put this in our activity, we'll understand it better. If electric current was in this direction and magnetic field was in this, then the force would be exerted in this direction. In the same way, if the direction of the current was changed, then the force did change its direction too. We should have to learn this rule because this rule will help us in finding the direction of the force in the equipment which works on the application of electromagnets. In our next video, we will discuss the principle and working of the electric motor.